Okay, hi and welcome to part 2 of video notes 8.7 exponential functions, day 1. So we covered all this here and we talked about what it is to be an exponential function and what differences were. And if we could find a constant rate of change in the first difference, we called that a linear function. And if we could find that our first difference wasn't constant and that there was a common ratio instead where we divided the y values, that meant that it was exponential. So in this section, we're going to be looking for those specifically, ones that have a constant, I keep saying constant, a common ratio. All right, so now that we have that down, we kind of know what all the different parts are, right? A is our initial value, B is our growth factor, and X is our number of periods or changes or events or time. It's all of the changing periods of it. If we know all those parts, let's look at a word problem here. So this one talks about an island of rabbits. There's 20 rabbits on this island, but the population triples every half year. And that's kind of every piece of the information, even though they give us the function right here, we could have written that without that function being there, because the 20 rabbits is our initial amount. That's always your A value, always. So whenever they say that here's an initial amount of rabbits or initial amount of dogs or bacteria or money, that's always going to be your A value. That'll always go out front. They should somewhere tell you a growth factor, something how it's growing. In this case, it's super easy. It's triples, which means 3. We'll talk about it in the next coming days if it doesn't go by doubles or triples or quadruples. If it's not an easy one like that, we'll see how to go ahead and write those up too. They're basically the same thing, just a little bit different. And then they tell us how frequently that takes place. So in this one, what we want to do is we want to go ahead and fill this out. Well, the only thing that we don't actually know is our x value there. But these are in half-year periods. So it says in the number of years here, right, there are half years at these populations. So every 6 months, essentially, these rabbits are tripling. So looking at this, we want to take 2 years, and how many half years are there in 2 years, right? So really, there's a half year, there's 2 half years in a year, or 4 half years. So I'm going to write down 4 half years. So when we do this problem, we're going to evaluate this, and remember f of x is function notation. We're going to plug in 4 here, because we want to find out after 4 half years, how many rabbits will there be if there's 20 to start, and they're tripling, so how many will there be after 4 half years? So we go ahead and stick that into our calculator. We'll move this right on over. These are ones that you'd put in your calculator. Don't necessarily have to put these in your head if it functions, which it's not. Let's close it and try it again. All right, so here we go. So we're going to type this in. We're going to type 20 times, or we can use parentheses there, 3, and then we're going to raise it to the 4th power, and it's going to tell us how many rabbits. So that's 1,620 rabbits is what we're going to find here. So again, after 2 years, 20 rabbits, tripling every half year, we're going to have 1,620 rabbits. You can see how fast exponential populations grow. So looking at the second problem here, you'll notice that the direction is to evaluate, which means plug a number in, get a number out. You'll notice that they say that these are domains, which in your head you know are x values. So we take all of these x values and plug them in. Just means we're plugging in 3 different x values. We're going to plug in -2, we're going to plug in 0, and we're going to plug in 3. These ones you could kind of do in your head if it's simple enough, and 5 to the x power is pretty basic. It's not too hard to follow. So we put 5 down as our base, because that's our base value, right? Our b is our base, and our exponent in this case is going to be -2. Well, we know exponent properties. We say negative moves it to the denominator and then square it. So that means put it in the denominator and square it. So 5 squared is 25, or 1/25. Kind of makes sense. So 5 to the 0 power, we know 0 power makes everything 1, so that's nice and easy. And then the next one's going to be 5 cubed, which is going to be 5 times 5, which is 25, times 5, which is 125. So nice and easy, nothing too complicated there. Do we get a point? Sure, a point's -2, 1/25, right? Or 0, 1, or 3, 125. Those are all points. That's really what we found. So it could say, hey, what are the ranges if it wanted to? Right? We've seen these before, and there's your ranges if you wanted to. There's your inputs, there's your outputs. And you can see there's another problem there for you to look at. All right, so let's go to the next page of our notes, which will look like this. And we're just going to talk about graphing these. One additional term we're going to throw in here is the word asymptote, but we'll talk about that once we see it a few times. You can see it's labeled on my graph already. So here's a graph. When you graph these, you're probably going to plot points or put them into your graphing calculator more often than not. While there is a pattern, the patterns change with the bases. And you'll notice this is a base 2, or doubling. This is a base 8, or it's changing by factors of 8. So each one of those gets its own pattern. So it's not as useful to memorize a pattern here, whereas it was for an absolute value, let's say. So this one, we just plug in the values. So 2 to the negative 1, right, just means switch its position, or 1/2. 2 to the 0 power, anything to the 0 power is 1. 2 to the first power, well, that's just 2 times itself once, which is 2. 2 squared is 2 times 2, which is 4. And 2 cubed, which is 2 times itself 3 times, or 8. And then there's your points, negative 1 and half. You can see that that's there, and you can see 0, 1, and you can see 1, 2, and you can see 2, 4, and you can see 3, 8. If I put it up here, which I didn't, we'll put 3, 8. I'm pretty close. I'm a little off there. So there's 3, 8. So that's how you would graph an exponential. You know by its shape what you should do. You should start slow somewhere, and it should increase. Okay, and there's the possibility that they may start high and decrease, but you know that there's going to be a sharp turn. So here's part of the thing you got to pay attention to. You might have to graph more points if you're having trouble seeing the function. Do not rely solely on 3 points. Don't put negative 1, 0, 1 in and be done. Make sure that you're putting more points in there if you can't see what the function looks like. So don't be afraid to do that. Sometimes when these happen, we know that they're exponential, and you can look here that they get really big, so they go off your graph. That's okay. You may use them as reference. And you should also know, and we'll talk about it now, is that they kind of level off. If you look at what happens here, this would just 1/2 here, and if we put negative 2 in, let's take a look at that. So it'd be 2 to the negative 2, or 1/4, right? Move its position and square it. You'll notice that they'll get smaller and smaller and smaller. Next one would be 1/8 at negative 3. So these are going to get infinitely closer. But really, what's happening? Well, they're cutting in half each time. Well, if I cut this in half an infinite amount of times, am I ever going to touch this purple line here, this what we're going to call asymptote? The answer is no. We're never going to touch that. We can't cut something in half so it becomes 0. And that's what's happening here. These are getting smaller and smaller and smaller, but they're never going to get small enough to reach to 0. There'll always be something there if we keep cutting it in half, and that's what's happening here. So that's what an asymptote is. It's a boundary that the function will never cross, and that function will never cross that. Now, don't get confused on this side. This function's increasing super high, and it looks very vertical, but it's always growing. It'll always get bigger. See, this will go to 5. This will go to 6. I can go infinitely down to my x values, and these values will continue to get bigger, right? And they'll get bigger and bigger and bigger, but I can keep going. It just goes up really fast. So that's the difference. There's not a vertical asymptote with these exponential functions, just a horizontal one. Okay, so looking at this one, you can see the horizontal asymptote here. It's the same. What's the difference between these two? Well, there's a base 2 and a base 8. So when it asks us down here, what does the increasing the base do to the graph? Well, let's look. Look at how this one's kind of curved. It's steeply curved, but look at that curve there. This one bends faster, right? Doesn't it start to increase faster? Which makes sense, because this one is 8 times 8 times 8. This one's only 2 times 2 times 2 as a base. So this one's growing fast, but not as fast as this one. So what would we say here? Well, we could say, how do they compare if we increase the base? Well, it increases faster. Okay, so that would be the first part. Are there any similarities? Well, if you were carefully watching, you might have noticed this, and I want you to pay attention to that. That they do have something in similarity, even though the other values aren't the same. This one is, which is the y-intercept. And we'll get to more of that, but there is a y-intercept is the same. And we'll look at that a little bit further in the next couple of days and see how that changes and see if we can always find the y-intercept, which I'm going to guess we can. All right, so here's another set of functions we'll take a quick peek at. Notice our bases this time, though. Our base is this number here, right? There's the exponent. You can see the x's. Our base this time is 1/2, which is a decimal, right? It's not greater than 1. It's between 1 and 0, and we'll talk about that in the next couple of days as well. But this one, look what happens to your function with this decimal here. It's starting really high, and it's decreasing really fast, and then it slows down. And the same thing happens over here. Even though it's coming from the negative side, it starts really negative, and then it slowly decreases and gets closer and closer and closer. And you can see it in the values. How can we do the values? Well, let's do them. It's super easy. Put 1/2 and put it to the negative 1 power, which means flip its flip its position, right? Move the positions, and then it becomes positive, or 2. And then 1/2 to the 0 power, well, that's anything to the 0 power is 1. And 1/2 to the 1 power, which doesn't change anything, it stays 1/2. 1/2 to the second power, or squared, is going to be square both. 1 squared is 1, 2 squared is 4, so it goes to 1/4. And then finally the next one, is a half, and that's cubed, so we get 1/8. And you can see that those points are plotted there. So it's getting infinitely close to 0, but it's never going to touch it, hence our asymptote. That's where that asymptote comes from. There's that boundary. How do we write those asymptotes? You can see that I wrote y equals 0. And if you remember from when we did lines, that we can write a horizontal line or a vertical line by remembering that whatever axis it goes through, we say that number that it goes through. In this case, it goes through 0, so we say y equals 0. If it was a vertical line through, I don't know, let's put one right here. If I was writing the equation for that one, it says -5 goes through -6. I would say it goes through the x-axis at -6. This is an equation of a line, not a solution, not a value, not a domain, not a range. It's an equation of a line because we said it was, and that's how you write horizontal and vertical lines. So your asymptotes will always have some form of y equals to them. They will always have that. So when we get over here, it's y equals 0. Now today's asymptotes are pretty boring, and here's another section of functions here to kind of show you that part. They're all at 0. They won't always be. In the next day or two of notes, you'll notice that they'll start to move, and you'll be able to write those, right? So let's see if we can answer these questions here. It says, what does multiplying a negative do to the base, or negative to the base do to the graph? Well, you can see here. Here's 1/2. Here's negative times 1/2 for our base, right? And this one decreases and it gets closer to the x. This one increases and gets closer to the x. But really, what's happening? It's just flipping. We took the function and we flipped it down. So we can just say it flips it. And we can even be more specific, flips over x-axis. And then we can be really specific. And we've seen that before with absolute values, so that's not too new to us. The next part says, what happens as a decimal as the base? Well, instead of increasing, because look at these, right? Here's a large value greater than a decimal. What happens? It starts slow from left to right, and it increases. Starts slow from left to right, and then it increases. Well, this does quite the opposite, right? It starts high, and it decreases really close to that asymptote, where it decreases slower and slower and slower. So what does the decimal of the base do? Well, it makes it decrease. All right, so we're getting some good information on these exponents now with these questions. Let's look at the final set here. And you can see the difference between these is our base is the same, right? There's 2. Our exponents are the same, right? X, we get to plug those in. But the only difference is we're changing the value that's being multiplied to it. Up here, we multiply by a negative, so we can see what a negative does. But this changes the value being multiplied to it. So let's take a look at that. Let's look at this first one here. This, if we cover up this 3 here real quick, is 2 to the x, which looks much like this one. So we can actually compare it to this first function here. Well, look what happens to it. Increases, it goes through 0, 1. We said that was a common point. They both went through 0, 1, which is nice, right? And it's got that shape. Well, this one has the same shape, but notice it doesn't go through 0, 1. Notice it kind of starts to pick up and curve before it goes through 0, 1. That was like the initial part of a curve. And look at how fast it's going right here at like 1. Look how high up it is. Where at 1, it's making its turn. Again, same function, but this one's being multiplied by 3. So what is this 3 doing? It's making it increase quicker, or sooner is actually the word that we want to use here. It's making it increase sooner. Well, let's make it larger. Let's make it 5. What is 5 doing? Well, look at 5. It's already increasing in turn. Look how high it is at 1, right? It's already up at 10. At 1 here, it's at 6. And at 1 here, because they're all the same, right? There's nothing multiplied to this one. At 1, it's 2. So it makes it increase sooner. It's the same curve, but it's just doing it sooner. It's starting it up a little bit faster. So what other questions here? Any patterns? Yeah, the number multiplied to the base is the same as the y-intercept. Oh, did you catch that? 3, y-intercept of 3. 5, y-intercept of 5. Let's go back up here to the top. 2 is really multiplied by a 1, or y-intercept of 1. Right here, 8 is really multiplied by 1, y-intercept of 1. So we notice how we said the y-intercept was same here. Now it's starting to make a little more sense. Whatever number our initial value, or the number that's multiplied to the base, ends up being our y-intercept. Okay, and again, is there a boundary that the exponential function will never cross? Yes, the asymptote, and that's the boundary where it gets really, really close to, but will never cross. It's called the asymptote. All right, so there's your notes. I don't want to cake them any longer than they already are, so I will see you tomorrow in class for some questions.